In this video, we're going to take a deeper look at Bohr's model of the atom. In the late 1800s and early 1900s, a new field of study in physics was developing. This was called quantum physics. It continued to develop and is now considered the field of modern physics. Quantum physics was necessary to describe the mathematics and observations of matter at the atomic and subatomic scale. What essentially was discovered is that there are different quote-unquote rules of physics depending on speed and size. Classical mechanics are the type of mechanics that we typically learn, so the laws of motion, laws involving electricity and magnetism, at scales that we commonly see at speeds far less than the speed of light. However, since we're looking at the atom, we're looking at sizes that are in fact quite small. And for this, we need a separate set of quote-unquote rules of physics. These are quantum mechanics. So classical mechanics are used to predict, observe, and explain the motion and behavior of large objects at non-relativistic speeds. Quantum mechanics, however, is used to describe matter at the atomic and subatomic scale. The rules of quantum mechanics often run contrary to the rules of classical mechanics, even though matter of different scale exists within the same universe. And we'll look at that a bit later when we discuss the quantum mechanical model of the atom. So in classical physics, radiant energy, so that is like the various forms of like radio waves, visible light, microwaves, infrared waves, X-rays, so on and so forth, was thought to be continuous. And according to classical physics, energy could be any value. It could be infinitely subdivided. But this led to some contradictions. In that model, if an electron is circulating around the nucleus, it should be constantly emitting energy. So according to the rules of classical physics, electrons circulating the nucleus of an atom should be constantly emitting energy. But if they were constantly emitting energy, then they would be constantly losing energy, and that would cause the electron to collapse into the nucleus. And this is often referred to as quote-unquote the death spiral of the electron. This doesn't happen, so as a result, we recognize that the rules of classical physics don't apply to something as small as an atom and an electron. So as a result, we have to turn to this new theory that was being developed, and it was originated by Max Planck. And what he stipulated, or what he said, was that radiant energy emitted by atoms occurs in a discrete bundle or packet called a quantum. So it's like energy is being emitted in like packages. And if you have multiple packages, these are called quanta. And a bundle packet of light energy is called a photon. Atoms can only absorb certain quanta, but they can absorb multiples of these quanta. So atoms absorb packets of energy. And these packets are so small that large-scale objects are unaffected by them. So we don't see what's called the quantum effect on the day-to-day scale that we live in. Bohr incorporated this quantum theory into his understanding of the atom. He built on Rutherford's model of the orbiting electrons around the nucleus, but he incorporated both quantum and potential energy. So he used the idea of potential energy in his model of the atom, and potential energy is also known as the energy of position. Since electrons are attracted to the nucleus, where protons are located, electrons being negative, protons being positive, the closer the electrons are to the nucleus, the lower their potential energy. As electrons move away from the nucleus, they increase in potential energy since they have the potential to fall back down to lower energy levels. An electron that has been infinitely removed from an atom, so electron has gained that quanta and has left the atom, no longer experiences the force of attraction to the nucleus. And that has been defined as having a potential energy of 0. Okay. So essentially that becomes like a reference point. So an electron that has been infinitely removed from the atom, so it's no longer part of the atom, it has a potential energy of 0. So the defined reference point of an electron not part of the atom has 0 joules of potential energy. Since this is the furthest away, 0 is your max value of potential energy. But as we said, as the electrons get closer to the nucleus, they lower in potential energy. As electrons move closer, the potential energy decreases. Therefore, potential energy values must be less than the maximum of 0. And if we think of what types of numbers are less than 0, well, those are negative numbers. So that's why we see a negative in terms of the potential energy of each of the energy levels. It's because the maximum energy an electron can have with respect to an atom is 0, and that's if the electron is not even part of the atom. It decreases in potential energy as it gets closer to the nucleus, and numbers that decrease from 0 are negative, and that is why we have negative potential energy of electrons. Bohr's first postulate was that electrons do not radiate energy while they orbit. So they're not giving off, constantly emitting energy. They stay at that potential energy while they orbit. So each orbit corresponds to a state of potential energy. And this is called a stationary state. So this is Bohr's very famous equation that he put forward through his observations. The energy of the electron at the nth energy level is given by negative r, which is your Rydberg constant, that's your constant of proportionality, divided by the n squared. And n is the principal quantum number, and it's the energy level. And you'll notice right here that n are just positive integers greater than 0. So an electron on the first energy level, we sub 1 into n, and we get this value. So all electrons in the first energy level are at this amount of potential energy. Electrons on the second energy level have this amount of potential energy, and so on and so forth. And as you can see, the potential energy increases because it's increasing towards 0 from a more negative. This right here is more negative. This right here is less negative. And the reason why it's less negative, if you look at the power of 10, this right here is closer to 0. Okay. Bohr's second postulate says that electron may only change its energy by jumping from one allowed energy level or stationary state to another. This is called the quantum leap, since the electron must absorb a quantity or a quantum of energy to do so. And that's where that word comes from, like a quantity of energy to do so. So in excitation, an electron moves from a lower energy level to higher. Okay. Energy is absorbed, and the type of energy that can be absorbed is heat, light, or electricity. In relaxation, it goes from a higher energy level to lower. And energy is released in the process of falling back down. And that energy is in the form of electromagnetic radiation. Essentially, Bohr incorporated quantum theory into his model by stating that the energy of an atom and the electrons within that atom is quantized. So what does this mean that the energy of an atom is quantized? This means that atoms can only absorb or release the exact amount of energy required for electrons to move from one potential energy or stationary state to another. If an atom is bombarded with quanta that do not match the exact value required for a quantum leap between energy levels, nothing will happen. So these are all the allowed transitions within the hydrogen atom. So you have electrons on the first energy level of the hydrogen atom, and if they absorb specifically this quanta or this packet of energy, they will jump from the first energy level to the second energy level. They don't stay there for long, they fall back down and they release the exact same amount of energy. They can also, if they absorb, again, another packet of energy, but this time the packet of energy is big and corresponds to the exact value of potential energy difference between the level of 3 and level of 1, it can make the jump up to the third energy level and then fall back down. So on and so forth. The other thing it can do is it can jump up to the first level and then absorb yet another packet of energy and jump up to the third. So it can do it in steps, just like the staircase. Jumps up to the first by absorbing a packet, then jumps up to the second, absorbing a packet, can fall back down to the second, and then fall back down to the first. So what is observed during these transitions? So in order to discuss the observations of these transitions, we have to look at the electromagnetic spectrum and the relationship between lambda, wavelength, and frequency. So we have these relationships that we previously discussed. That if E is equal to HF, that means that E is proportional to F. The higher the energy, the higher the frequency. We also know that C is equal to lambda F, and so therefore C over lambda is equal to F, and therefore F is proportional to 1 over lambda, or inversely proportional to lambda. The other thing that we have is we have that energy is inversely proportional to 1 over lambda, which we previously saw. So the shorter the wavelength, the more amount of energy. So as you can see here, the visible light only ranges from 400 nanometers to 700 nanometers. These are the wavelengths of visible light, 400 being violet and 700 being red. So your visible light only falls within this range right here. If your wavelength is less than 400, then you're looking at UV rays, which our eyes cannot perceive. If you go less than 10, then we're dealing with X-rays, so on and so forth. If the wavelength of light is beyond 700 nanometers, then we're looking at infrared light. Again, our eyes can't perceive this. So only wavelengths between 400 nanometers and 700 nanometers are going to be, we can perceive with our eyes. Going back to this diagram up here, if you can see right here, falls that go from 2 to 1, 3 to 1, 4 to 1, 5 to 1, those are very big falls, very high energy. Because they're very high energy, that means they have short wavelength. Short wavelength would put it in the UV spectrum. And so we cannot perceive these transitions of relaxations of light. But if an electron can fall between 3 to 2, 4 to 2, 5 to 2, and 6 to 2, those are transitions that we can see. This right here is a very small fall right there, so that's not very much energy. So energy there would be quite low. If energy is low, that means we have a longer wavelength, so this fall would produce red light. This fall right here is big enough that it still falls within the visible range, but there's much more energy, so this produces violet light. These falls can also take place as well, or these excitations and relaxations can take place as well, but they are so small that the energy is also very small, and therefore the wavelength is quite long, and that would put them in the infrared spectrum, which we cannot see. So these are the transitions that are taking place within the hydrogen atom, but only 4 of the transitions do the cells in our eyes have the ability to see. So even though all these other transitions are taking place, humans can only perceive these 4 transitions because those are the transitions that are perceptible to our eyes. Let's continue. The part of light that we can see is the visible light spectrum. White light is composed of all the frequencies of visible light, the continuous spectrum of light, and that ranges from 400 nanometers to 700 nanometers. When we have excitation and relaxation of hydrogen, again, I said we can only see 4 lines that correspond to the transition between 3 to 2, 4 to 2, 5 to 2, and 6 to 2. And those transitions produce the following wavelengths: 410, 433, 486, 456. These right here are the wavelengths. These are the lambdas of visible light for hydrogen right here. 410 being on the lower end corresponds to violet. 433 or 434 corresponds to indigo. 486, the cyan color, and 656 is red. Even though many other transitions are possible and are happening, we only see 4 lines because they fall in the visible range. They are called the Balmer series of transitions. So which transition series is most likely to release UV photons? Well, we have that in our diagram right here if we go back to it. The transitions of 2 to 1, 3 to 1, 4 to 1, 5 to 1, those are very big jumps, releasing a lot of energy, and those more will correspond to the ultraviolet range of light. This is called the Lyman series, and the Paskin series is infrared because those are very small, and therefore small transitions, small energy, longer wavelength in the infrared spectrum. So the Lyman series is the series that produces UV photons, and the Paskin series is the series that is likely to release infrared photons. Okay, so spectroscopy is used in a lot of different areas, and it just basically analyzes the way matter absorbs or releases energy. Spectroscopy is used to identify elements or compounds through atomic spectra, okay, and this means that each element has a unique set of wavelengths it releases / absorbs. We can see hydrogen has these 4 wavelengths right here that it absorbs, but other elements have other wavelengths that are absorbed and released. We can obtain information about bonding and the structure of compounds by looking at how the electrons within bonds absorb energy. And we can quantitatively determine the concentrations of substances present using spectroscopy. So the darker a solution is, the more photons are absorbed, right? And that means that there's more substance present. There are 2 main types of atomic spectrum. You have an absorption spectrum and an emission spectrum. Okay. The bright line spectrum is a specific term used for the emission spectrum within the visible light range is your bright line spectrum. So looking at an absorption spectrum, this is an absorption spectrum right here. is when you shine white light on an element and you look at the other side of the element, the gaseous element, lines will be missing, and those are the wavelengths of light that were absorbed. So this corresponds to excitation. Okay, these are the wavelengths of light absorbed for excitation. The emission spectrum corresponds to relaxation. So emission spectrum is the wavelengths of light released during relaxation. The continuous spectrum contains all the frequencies of visible light. So you can see that the absorption spectrum is essentially the continuous spectrum, missing the frequencies of light that were absorbed by the electrons in the element to make those jumps up. The emission spectrum is the wavelengths of light that were released when the electrons fall back down. So Bohr's model was great. It effectively was very good at predicting the wavelengths of light released or absorbed by hydrogen during excitation and relaxation. Relaxation. Okay. It also was very good at agreeing with Mendeleev's periodic law. So we can write here that it confirmed Mendeleev's periodic law, and that is that elements repeat in physical and chemical behavior based on the number of electrons present. All right, so Mendeleev was a scientist, if you're not familiar with this, that developed the periodic table similar to how we see it currently. And so by positioning, for example, all the alkali metals on top of each other, they were all chemically reactive with water. They're all very highly reactive. They're softer metals. This corresponds to Bohr's model of the atom because all of those metals only have one valence electron. Similarly, noble gases, very unreactive. Those were all grouped together within a column according to Mendeleev's periodic law, further explained by Bohr's model of the atom, in which they had full outer shells and therefore were unreactive. So his model was quite good at confirming this periodic law and again at really predicting the wavelengths of light that were absorbed and released by hydrogen. Now the big problem is that it only worked for hydrogen in terms of his spectroscopy. So this portion right here only really worked for hydrogen, and it got worse. Worse with increasing number of protons/electrons. So Bohr's model, its ability to predict the wavelengths of light that were released during relaxation, that just got worse as we went to helium, lithium, and so on. Okay. All right, so that is the essence of Bohr's model of the atom, and just a deeper dive on excitation and relaxation and how it relates to the electromagnetic spectrum.